Have you ever looked up at a storm and wished it was raining something a little more valuable? Here on Earth, a shower of priceless gems is pure fantasy. But what if I told you that on planets not that far from us, it rains actual diamonds? This isn't science fiction. Deep inside the swirling, chaotic atmospheres of the ice giants in our own solar system, a constant glittering storm of diamonds is falling. We're talking about a celestial phenomenon where the weather forecast is, quite literally, priceless. But the story doesn't stop there. What if this cosmic bling isn't just a weird weather pattern on a couple of distant planets? What if there are worlds out there scattered across the galaxy made almost entirely of diamond? Planets where mountains are carved from diamond and canyons are etched into fields of graphite. It sounds like a treasure hunter's wildest dream, but science is telling us these places could be real. Today, we're taking a journey from the bizarre weather of our neighbors to the farthest reaches of space to uncover the science behind worlds where diamonds are as common as rocks. At Part 1, the diamond downpour on Earth, a what-if scenario. Before we rocket off to the gas giants, let's just imagine for a second. What if you woke up one morning not to the patter of water, but to the sharp clink of falling diamonds? The first thing you'd notice wouldn't be the sparkle, it'd be the destruction. Raindrops are gentle. A diamond, the hardest natural substance we know, is anything but. Even a small 1-carat diamond falling from cloud height would hit the ground with the force of a bullet. Your roof wouldn't stand a chance. Cars would be dented and shattered. Just walking outside would be life-threatening without some serious protective gear. And the economy? You might think you're rich, scooping up a fortune from your front lawn. But when something becomes that abundant, its value plummets. The global diamond market, which is built on the idea of scarcity, would collapse overnight. Diamonds would become worthless. We'd start using them for what they're really good at on an industrial scale, as abrasives. Diamond-tipped saw blades would be cheap, and we'd probably crush them up to pave our roads, creating glittering, shimmering highways. The environmental impact would be staggering. Unlike water, diamonds don't flow. They'd just pile up, creating massive, glittering dunes of sharp crystals. Rivers would be dammed, landscapes totally reshaped, and farms buried under a layer of indestructible gems. Life on Earth depends on the water cycle. A diamond cycle would just be a cycle of pure, unrelenting abrasion. So, while it's a fun thought, a diamond downpour on Earth would be a beautiful, sparkling catastrophe. Luckily for us, the conditions for this don't exist on our planet. To find a real diamond storm, we have to go much, much further from home. Chet, Part 2, a journey to the ice giants. Our first stop, the mysterious outer suburbs of our solar system, home to the ice giants, Uranus and Neptune. These aren't just cold, distant worlds. They're colossal spheres of gas and exotic ice, swirling with secrets. From here, Neptune is just a faint blue dot, a peaceful-looking orb in the blackness of space. But that calm exterior hides a truly violent and alien interior. Over 4.5 billion kilometers from the Sun, Neptune is a world of unimaginable extremes. Its atmosphere is a chaotic mix of hydrogen, helium, and a little methane, which is what gives the planet its signature blue color. And that methane holds the key. Winds on Neptune are the fastest in the solar system, screaming at over 2,000 kilometers per hour. That's faster than the speed of sound on Earth. Giant storms, the size of our entire planet, rage across its surface and then just disappear. But the wildest weather isn't on the surface, it's deep inside. To understand what's happening, we have to go thousands of kilometers below the cloud tops, into Arium, where the rules of physics are pushed to their absolute limits. Uranus, Neptune's slightly larger and less blue twin, tells a similar story. It's a tilted giant, knocked on its side by a cosmic collision ages ago, so its seasons last for decades. And like Neptune, its atmosphere is rich in the right ingredients for something spectacular. For decades, scientists theorized that deep within these two planets, something incredible was happening. They crunched the numbers, they built the models, and they all pointed to one unbelievable conclusion. On Uranus and Neptune, it is literally raining diamonds. at Part 3, The Science of Diamond Rain, a Cosmic Recipe. So how is that even possible? How does a planet create a non-stop storm of diamonds? It's not magic. It's a simple recipe with some very extreme ingredients. The key ingredient, as we said, is methane. Methane is a simple molecule, CH4, one carbon atom bonded to 4 hydrogen atoms. And it's everywhere in the atmospheres of the ice giants. Now for the other 2 ingredients, immense pressure and intense heat. As you go deeper into Neptune or Uranus, the weight of the atmosphere above becomes crushing. About 10,000 kilometers below the surface, the pressure is millions of times greater than here on Earth. At the same time, the temperature soars to thousands of degrees Celsius. Under these hellish conditions, methane molecules just can't hold together. The pressure squeezes them apart, breaking the bonds between the carbon and hydrogen. The hydrogen atoms are stripped away, leaving the carbon atoms all by themselves. Surrounded by that immense pressure, these newly freed carbon atoms have nowhere to go. So they do the only thing they can. They start linking together. This is where the chemistry happens. The pressure forces the carbon atoms to arrange themselves into an incredibly strong, tightly packed crystal structure, the lattice of a diamond. Atom by atom, a diamond is born. But it doesn't just stay put. Because solid diamond is denser than the soupy fluid mix of water, ammonia, and methane around it, it starts to sink. It falls, like a raindrop through air, or maybe more like a pebble through water. And this isn't just a few diamonds. Scientists believe it's a constant process, creating a continuous rain of diamonds, falling from the upper layers of the mantle down toward the planet's core. Researchers predict these diamonds could grow to be enormous as they sink, maybe weighing millions of carats after descending for thousands of years. Here, Part 4, The Proof, Recreating Alien Worlds in the Lab. A story about diamond rain on distant planets is one thing, but how can scientists be so sure? We've never sent a probe that deep. The answer lies in some of the most advanced labs on Earth, where researchers have recreated the extreme conditions of the ice giants. At facilities like the SLAC National Accelerator Laboratory and the European XFEL, they've run some mind-bending experiments to test this very idea. The challenge is creating those pressures and temperatures, even for a fraction of a second. To do it, they use a device called a diamond anvil cell, basically a tiny vise that uses the tips of 2 flawless diamonds to squeeze a sample with incredible force. The sample they use isn't methane gas, but a type of plastic like polystyrene or PET, the same stuff in plastic bottles. This plastic is a hydrocarbon, made of hydrogen and carbon, perfectly mimicking methane's chemistry deep inside the ice giants. Once the sample is squeezed, scientists blast it with a high-powered laser. This creates a shockwave that skyrockets the pressure and temperature, replicating Neptune's interior for just a few nanoseconds. But how do you see what happens in that instant? You hit it with something even more powerful, one of the world's brightest X-ray lasers. The X-ray beam scatters as it passes through, telling scientists the atomic structure of the material inside. And in experiment after experiment, they saw it, the unmistakable signature of carbon atoms snapping into the crystal lattice of diamonds. They were literally watching nano-diamonds form in real time. More recent studies published in early 2024 have refined this even further. Researchers found that diamond formation happens at even lower pressures and temperatures than they first thought. This means the diamond rain probably starts much shallower inside Uranus and Neptune. They also made another fascinating discovery about oxygen. When they used a plastic that also contained oxygen, they found it acted as a catalyst, speeding up the process and allowing diamonds to form even more easily. This suggests that diamond rain could be an even more common process on ice giants than we ever imagined. Part 5. More than just bling, a planet-shaping phenomenon. The idea of diamond rain is spectacular, but it also means a lot more for how these planets work. First, it could be an internal heat source. As these newly formed diamonds, some potentially millions of carats in size, sink through the mantle, they create friction. That friction generates heat. This could finally explain a long-standing mystery: why Neptune radiates more than twice the energy it gets from the sun. A constant shower of diamonds powering an internal heat engine could be the source of that extra energy, driving the planet's violent storms and supersonic winds. Even more profoundly, diamond rain might solve the puzzle of the ice giant's bizarre magnetic fields. Unlike Earth's, which is pretty neatly aligned with our axis of rotation, the magnetic fields of Uranus and Neptune are wild. They're tilted at crazy angles and are shockingly off-center, as if the magnet inside the planet was just tossed in there haphazardly. Scientists now think the diamond rain is directly responsible. Recent findings suggest that as the diamonds fall, they drag layers of gas and conductive superionic ice along with them. This superionic ice is a strange phase of water that only exists under extreme heat and pressure, where water molecules break apart and hydrogen ions can flow freely, conducting electricity. The falling diamonds stir up this conductive slush, creating powerful currents. These swirling electrically charged currents then generate the planet's magnetic fields. Because this is all happening in a specific layer of the mantle, not at the core, it creates a field that is lopsided and chaotic, a perfect match for what the Voyager 2 spacecraft saw. So the diamonds aren't just falling, they're actively shaping the planet's energy and its magnetic field. Part 6, a never-ending diamond storm? So what happens to all these diamonds? Do they just pile up at the core, forming a diamond layer thousands of kilometers thick? For a while, that was the leading theory, a solid shell of diamond larger than the entire Earth, blanketing the planet's rocky core. But some models suggest an even more dynamic cyclical process. The cores of these ice giants are incredibly hot, possibly hotter than the surface of the sun. As the diamonds sink closer to this scorching core, they might not stay solid. Even a diamond can melt or vaporize at those temperatures, turning back into a dense carbon-rich fluid. If that happens, it would create a remarkable cycle. This carbon fluid, now less dense than the solid material at the core, would rise back up through the mantle in convection currents. It would travel into cooler, lower-pressure regions, crystallize into new diamonds, and begin its long fall all over again. It would be a planet-wide geological cycle, like the water cycle on Earth, but with diamonds. A constant, self-sustaining storm where diamonds form, rain down, melt, and then rise to form again. Chapter Part 7, Beyond Our Solar System, the Cosmic Bling. Discovering diamond rain on our own neighbors was a game-changer. It proved that the universe was far stranger than we had imagined. But what if this isn't just limited to our solar system? The same research that confirmed diamond rain on Neptune also suggested it could be happening on a whole class of exoplanets known as mini-Neptunes. These are planets smaller than Neptune but larger than Earth, and they're one of the most common types we've found so far. With potentially thousands of these worlds scattered across the galaxy, diamond rain could be a widespread cosmic phenomenon. But the universe doesn't stop at diamond rain. It has something even more spectacular in store. What if a planet wasn't just experiencing diamond weather, but was, in its very essence, a diamond? To find these ultimate treasure worlds, we have to look for a very specific kind of solar system. It all comes down to the chemical recipe of the star itself. In most of the galaxy, including our solar system, there's more oxygen than carbon. That leads to rocky planets like Earth, which are mostly made of silicates, compounds of silicon and oxygen. But what if a star system formed in a pocket of space where that ratio was flipped? What if there was more carbon than oxygen? At Part 8, the ultimate treasure planets. In regions of the galaxy with a high carbon-to-oxygen ratio, the chemistry of planet formation gets turned on its head. Instead of silicate rocks, the primordial dust grains in the disk around the star would be made of carbon-rich materials like graphite and silicon carbide. When these grains clump together to form planets, you don't get an Earth. You get a carbon planet. A carbon planet would be a world almost beyond comprehension. It would likely have an iron-rich core like Earth, but that's where the similarities end. The mantle wouldn't be molten silicate rock, it'd be a sea of molten carbides. Above that would be a thick crust of graphite. And if the planet is massive enough, the immense pressure in its interior would do something incredible. A huge portion of its mantle, a layer potentially thousands of kilometers thick, would be compressed into pure solid diamond. These aren't planets with a few diamonds. These are planets that are diamonds. Volcanoes on such a world wouldn't spew lava. They might erupt liquid carbides that cool into mountains of diamond and silicon carbide. Any surface liquids would be tar-like hydrocarbons instead of water. The atmosphere would likely be a toxic smog of carbon monoxide and methane. It would be a dark, glittering world, a planetary-sized jewel box. The famous exoplanet 55 Cancri E, a super-Earth just 40 light-years away, was once thought to be a prime candidate for a diamond planet, sparking the imagination of scientists and the public. At Part 9, the hunt for diamond worlds. So how do we find these exotic worlds? It starts by looking at the stars. By analyzing a star's light, astronomers can determine its chemical composition. If a star has a carbon-to-oxygen ratio greater than about 0.8, it's a good candidate for hosting carbon-rich planets. And these might not be that rare. Some estimates suggest 12 to 17% of stars in our galaxy could have the right chemical mix. That means for every 10 stars you see in the night sky, 1 or 2 of them might be hosting a world made of diamond. Once a candidate star is found, the hunt for planets begins. Astronomers use methods like the transit method, looking for a tiny dip in the star's light as a planet passes in front, to find these worlds. The James Webb Space Telescope has become an invaluable tool in this search, able to not only detect planets, but also analyze their atmospheres. A whiff of gases like carbon monoxide and methane, with a distinct lack of water vapor, could be a telltale sign of a carbon planet's chemistry. New discoveries are constantly challenging our models. In late 2025, astronomers using the Webb telescope studied a planet-forming disk that was shockingly rich in carbon dioxide, but had almost no water. Discoveries like this show that the building blocks for planets can be vastly different from what we see in our own solar system, opening the door for even more exotic worlds we haven't even imagined. The hunt is on, and every new exoplanet brings us closer to confirming the existence of a true diamond world. Part 10, Recipe for a Diamond Planet. The theory of diamond planets isn't just a guess. It's backed by lab experiments similar to the ones that proved diamond rain. Researchers at Arizona State University wanted to see what would happen to the raw materials of a carbon planet under intense pressure. They started with silicon carbide, a primary building block of these worlds, and added water, which is abundant in the universe. Using a diamond anvil cell to create extreme pressure and lasers to heat the sample, they watched the chemistry unfold. The results were transformative. The silicon carbide reacted with the water, breaking down and reforming into 2 new substances, silica and pure diamond. This experiment provided the crucial evidence that if a carbon-rich protoplanet has water around when it forms, its interior will naturally separate into a diamond and silica-rich mantle. The planet essentially cooks itself into a diamond. This process would fundamentally change everything about the planet, from its density and mass to its potential for having a magnetic field or plate tectonics. It solidifies the idea that carbon-rich exoplanets aren't just a possibility, but a likely outcome in the right environments. The universe, it seems, has a recipe for creating the most valuable worlds imaginable. At Part 11, A Universe of Wonders. The existence of diamond rain and diamond planets shatters our Earth-centric view of what a planet can be. It proves that the cosmos is a place of infinite variety. And diamonds are just the beginning. The universe is a chemical playground, and under the right conditions, all sorts of bizarre weather can happen. Imagine a planet where it doesn't rain water, but iron. On some hot Jupiter exoplanets that orbit incredibly close to their stars, the day side is so hot that metals like iron vaporize into the atmosphere. These metallic clouds then drift to the cooler night side, where the iron condenses and falls as a shower of molten metal. And it gets weirder. There are exoplanets where scientists think it might rain sapphires and rubies. On a planet like HAT P7b, the clouds are thought to be made of corundum, the mineral that forms these gems. Under the right conditions, these clouds could produce a rain of red rubies and blue sapphires, painting the sky with a storm of jewels. From iron storms to jewel showers to diamond deluges, These phenomena show us that our own weather is just one possibility among countless others. Each new discovery of weird weather or an exotic planet is a reminder that the universe is not only stranger than we imagine, it is stranger than we can imagine. We started with a daydream. What if it rained diamonds? We've journeyed from that fantasy to the scientific reality happening deep inside Neptune and Uranus, where a constant shower of gems helps shape those very worlds. We've seen how scientists can prove it by recreating these alien conditions right here in a lab. And then we ventured further, across the galaxy, to find that the universe's creativity doesn't stop there. It has a recipe for entire planets made of diamond. These discoveries do more than just add to our collection of cosmic oddities. They completely change our understanding of what a planet can be. They show us that the laws of physics can produce outcomes that feel like they belong in a myth or a fairy tale. The universe is a vast and mysterious place, and we're only just beginning to read the first few pages of its story. For every question we answer, a dozen more pop up. What other impossible treasures are raining down on distant worlds? What other unbelievable planets are waiting to be found? The search continues, but one thing is clear. The cosmos is filled with more beauty, more strangeness, and more diamonds than we ever dared to dream. Would you want to live on a planet where it rains diamonds? Let us know your thoughts in the comments below. And if you enjoyed this journey into the cosmos, don't forget to like this video and subscribe for more mind-blowing space facts. Thanks for watching.